Hello everybody and welcome to the third video in this Pygame car racing tutorial series. In this video, I'll be implementing the computer car. So we're going to set up a path for this car to follow along with, and then we're going to make it follow the path, which is much more complicated than it seems. Let's get started. So the first thing I want to do here is make a class for my computer car. So I'm going to say class computer car like that. It's going to inherit from abstract car. And then inside of here, I'm going to define the image for my car as well as the starting position. So I'm going to say image is equal to, and this will be the green car, and the starting position will be 150. Okay, that's pretty straightforward for the computer car. Next, I'm going to override the initialization. So I'm going to say define init self. This is going to be max vel and rotation vel. Is giving me that. Very good. And then I'm also going to take in a path, which is going to be equal to an empty list by default. Then what I'm going to say is self dot, not self actually, super dot underscore underscore init underscore underscore, and I'm going to pass the max velocity and the rotation vel. What this is going to do is use this method right here to initialize all of the values that I need, and then I'm just going to initialize a few more under here. I'm going to say self dot path is equal to path. Path is going to be a list of coordinates of points that I want my car to move to. And I'm going to say self.current underscore point is equal to 0 because I need to know what point in my path I'm currently at. Then I'm going to say self.vel is equal to the maximum velocity because my computer car, we don't need to worry about acceleration. It's just going to immediately start at the maximum velocity and will move at that speed the entire time. Okay, now we have the computer car. The next thing I want to do is just implement a method on this car that can draw all of the points in the path, just because this will be useful for us to visualize. So I'm going to say define draw points, and then I'm going to say self, and we'll take in a window, and I'm going to say for point in self dot path. I guess we could have called that points too, but that's fine. And then we'll say Pygame dot draw dot circle. And we'll draw this on our window. We need to pass the color of our circle, which is going to be red. So in Pygame, the colors are RGB, so red, green, blue. So 255 is full red, 0 green, 0 blue. Then I'm going to pass the point. This is going to be the center of the circle that I want to draw. And then the radius will go with 5. So that means we're going to have a diameter of 10 for our circle. So that should draw all of the points for us. That's pretty straightforward. Okay, now we have draw points. Next, I want to make some feature that allows us to actually kind of click on the screen and, I guess, draw, create, select all of the points for our path. So that way we don't have to manually add them inside of this path variable. So you'll see what I mean in a second, but first let's create a car. Let's go computer underscore car is equal to computer car. We need to pass a maximum velocity and a rotation velocity. So for now, let's just go with 4, we'll match our player, although we will reduce this later. And then for the path, we won't pass anything right now because we're going to kind of dynamically create the path. Okay, so now we've made computer car. Let's draw it. So let's pass computer car to our draw function, and then let's go to draw. Let's take in computer car, and let's do computer car dot draw. And inside of here, let's draw on the window. And then what we will do is we will override the draw method in here. So we'll say define draw self win. We'll then say super dot draw. So we'll call the draw method from the abstract class here. So we'll do this. But before we do that, we will draw all the points, or after, it doesn't really matter, but we'll draw all the points. So we'll say super dot draw. We need to pass the win, and then we'll say self dot draw points and the window. So now when we draw our computer, it will also draw all of the points in the path for this AI computer, whatever. Okay, there we go. Now that we have that, let's just run the code and see if the computer is being drawn, and then we will continue. Okay, great. So the computer car is there. That's all we were looking for. Okay, let me clear the console here. Now let's continue. So the next thing I want to do is make it so we can click with the mouse, and that adds a point to our computer's path, and then we can get all of those points at the end of the program so that we don't have to manually write them. This is pretty easy. I'm going to go inside of my event loop here. So for event in pygame.event.get, I'm going to say if event.type equals pygame dot, this is going to be mouse button down like that. Then what we're going to do is get the position of the mouse. We're going to say pause is equal to pygame.mouse.get_pause. And this will give us the XY coordinate of our mouse on the Pygame screen. Then we will say computer car dot path dot append position. So we'll add that position to the computer's path. Okay, that's really all we need to do, except at the end of our program, we're just going to print out the computer car dot path just so that we can copy it and then save it in our file and use it for future use. So let's run the code and let's see what we get here. Okay, we get our computer car. Now let's start adding some points. So I'm going to add one here. I'm going to add one here. And I will just add all of these. And then once I'm done, I will be right back. Okay, so I've added all of my points here. You can see this is kind of the path that I've defined. I've tried to spread them out as much as possible, but it doesn't really matter. I mean, just add the points and make them on the track, and you'll be good. You could put them off the track because we're not checking collision with the walls, but obviously the better you make your points, the better this is going to be. Now, I recommend you do spread them out a bit. If you make them too close, you're going to see it's going to look like all jittery when we're kind of turning and angling towards them. Anyways, that's fine. Okay, so let's close this. And notice when I close this, it prints out all the points. So what I'm going to do is copy all the points. And I'm just going to make a variable at the top of my program here called path. And I'm going to have it store all of these points, just so that I can use this with my computer, right? With my computer car. So now what I will do is I will actually go to where I initialized my computer and I will pass that path. So now that will be set for my computer. And then I'm going to get rid of this mouse button down logic because I no longer need that because my path has been set. So now that I have the path, let's just run this. And notice the path is still printing out. It's, saved, right? Because I have it in a variable. Great. And then, of course, my red car can continue to move just like it did before. Awesome. So now that we have that, what I want to do is hop over to Paint. And I want to show you or discuss how we're actually going to kind of solve this problem of moving the computer car towards these points. And it's pretty complicated to do this, but I will try my best to explain. So let's say our target point is right here, and our computer is right here, okay? This is our computer car. So let's just go see, this is car. Now, the first thing that's kind of intuitive to do here is to draw a line between the top left-hand corner and the point that we want to get to. Now, we're going to be using the XY as the top left-hand corner of our car, so keep that in mind. That is pretty important for this. And anyways, there we go. So we have our target, and we have, our car. Now, how do we get to this point? Well, the first thing we can do is we can calculate the displacement in X and the displacement in Y, right? So we know the velocity, but we do not know the angle. And so what we're actually going to want to look for here is the angle between our computer and this point. If we know the angle, then we can tilt our car to that angle, and then we can move in that direction. Easier said than done, but that's the goal. We want to find the angle between our car and the point that we want to get to, and then we want to set the car so that it's facing that direction, and then just move the car in the same way that we moved our player car, because we already know how to move the player car, right? That part is done. We've implemented that logic. So anyways, we have X and we have Y. Now, we can easily calculate X and Y because we know the coordinates of this point and we know the coordinates of this point. We would just take this point's X, subtract by this point's X. That gives us the displacement in X. This point's Y, subtract by this point's Y. That gives us the displacement in Y. Now, it doesn't really matter if we get negative or positive values. We could take the absolute value if we want, but it doesn't matter if we get negative or positive, okay? Finding the angle is still going to be the same. And then we have our velocity. Now, the velocity we don't really need to use, but we know the velocity is going to be the hypotenuse of the triangle. Okay, that's fine. So what we're trying to do here is determine the angle. We know X, Y, and V, so there's multiple ways to do this. Now, remember our equations are this is going to be an H. Let me erase that. So, Ka, and then TOA. Now, in this case, it seems intuitive to me to use TOA because we know the opposite and we know the adjacent. So what we can do if we want to solve for theta, which is the angle that we're looking for, is we can write the equation tan, and then this is going to be of theta, is equal to O over A. Now, we can do our substitutions, and when we do our substitutions, we see that O is Y and that A is X. So we know X and Y, those are two variables that we know. So now we want to solve for theta. So any of you that know trigonometry know that we have to take the inverse tangent of this, and then that will give us theta. So we can say theta is equal to, and then tan inverse of y over x. And then that will give us the angle that we're looking for. And in fact, this is actually always going to give us what's known as an acute angle. Now, an acute angle is any angle that's less than 90 degrees. Now, it will give us either a positive or negative acute angle. So we could get a negative value here or a positive value here. If we get a negative value here, that's indicating to us that we are looking to the left. If we get a positive value, then to the right. Anyways, that's not super important right now, but just keep in mind that this is how you calculate theta and that this is always going to give us an acute angle. That is important. It's always going to give us something based on the way we're doing this calculation that is less than 90 degrees. Okay, so now we have found the angle. So we found the angle between our car and our point. So it should be simple enough, right? Just set the car at that angle. Well, it's not quite that simple. The reason why it's not quite that simple is because if our car is like facing this direction and we want to go over here, if I just set its angle to that, it's going to look like it's just teleporting over. That would be the easy solution. Just set the angle and then that'd be fine. But if we do that, what happens is, first of all, we're going to have our car facing the wrong direction a lot of times. We're also going to have the car flipping instantly, which we don't want. We want it to kind of slowly transition to that angle by its rotational velocity. We don't want it to just teleport over and face that direction. So now comes the problem. Okay, we know that angle. We know the angle our car is currently facing. How do we determine what direction to turn the car to get to that angle? That's really the problem now. We know the angle. We know the angle of our car. Now we just need to actually make this car get to that angle. So there's a few problems here. Again, the first problem is that we need to make sure we aren't just teleporting. So we have to kind of decide, do we want to go to the left or do we want to go to the right? Now, this might seem easy when you're looking at an angle like this, but there's so many different angles we could possibly have. And sometimes we could take the unoptimal approach if we only ever went to the left or only ever went to the right when trying to get to these angles. So for example, let's say we have this. Okay, let's just move this over a bit. Let's say our target angle is here. Okay, and our car is facing this way. So car is black and the target angle is red. Now, what way should we turn to get to this target angle? Well, we should turn this way. However, we might end up turning this way. So this is kind of the problem. We need to figure out which way to turn. Now, another problem that we're going to run into potentially here is that we might have the angle be here. So let's imagine this guy is gone, okay? We might have it be here. Now, theoretically, me turning like this is actually going to make it look like we have the same angle. I know this seems really weird, but the way that this angle is calculated means that this could actually be this, or other way around. We could get this angle from this. So we need to kind of put in some checks here to ensure that if we're actually moving downwards, we're actually going to go in the downward direction. We're not going to mistakenly calculate this angle. The reason why this is a problem is because these two angles are the same, right? If you look at this angle and you look at this angle, they're the same. And so when I do the tangent based on the way that I'm doing it, I could get this when my point is down here. And so I need to make sure that I'm actually looking at what direction my point is in, if it's lower or higher than where I am. And based on that, I'm going to need to make an adjustment to the angle I get to ensure that I'm going the right direction. So I'm just trying to kind of point out some of the problems that you can run into doing this. And there's all kinds of other problems as well. For example, right, like I was saying, we might go and try to go like this when instead it would be more efficient to go like this. So if we ever have a very large angle, we'll actually want to reduce that angle to a smaller yet equivalent angle so that we end up moving in the, I guess, best direction, the quickest direction to get to it. I also realized that all of my lights turned off here. I'm just going to turn them back on. I'm sure you guys can still see my face fine, but I have like these background lights that for some reason went off. Okay, so that's a bit better. Okay, anyways, that was kind of the point of this. I'm sure this hasn't cleared everything up. I haven't necessarily stated the solution. I just wanted to show you problems that can happen. And really the main problem is, what direction do we go? Do we go left or right? That's the main idea. So let's now start trying to implement this. So we will continue in 1 second, but I need to quickly thank the sponsor of this video and this series, which is Algoexpert. Algoexpert is the best platform to use when preparing for your software engineering coding interviews. Not only do they have a ton of coding interview practice questions, they also have mock interviews, a data structures crash course, and a bunch of other awesome features to help you prepare to land your dream software engineering job. With that said, check out Algoexpert from the link in the description and use the code TechWithTim for a discount on the platform. I'm going to go into computer car, and I'm just going to define a move method. Now, this move method is special because when I'm moving, I need to move towards a point. So the first thing I need to do is angle the car in the correct direction. And if I am in the correct direction, then I can start moving towards that point. And we already know how to move. We can just use the move method that we have inside of here, right? If we're angled in the right direction and we're going by a static velocity, then that's fine. So I need to look at my other code here because it's very easy to mess this up. So inside of move, what I'm going to do is just make sure that we have a point to move to. I'm going to say if the self.current point is greater than or equal to the len of self.path, then I'm going to return. This is just going to ensure that we are not going to get an index error by trying to move to a point that doesn't exist. That's the point of this line. After that, I'm going to say self.calculate, and this is going to be angle. Now, we will write this method in a second, but this is going to calculate the angle and shift our car in that direction. The next thing we're going to do is say self.update underscore path underscore point. Now, what this is going to do is see if we need to move to the next point, because as soon as we hit a point, we collide with that point, we then move to the next one. That's it. And then here, we're going to say super.move. So we're going to actually call manually the move method that we're overriding inside of car. Okay, so let's start by implementing calculate area or calculate angle. I'm going to say define calculate angle self. The first thing I want to do is calculate the displacement in X and Y between the target point and my current position. Once I do that, then I can find the angle between my car and the point, and then I can adjust the position or angle of my car accordingly to move towards that target point. So I'm going to say target underscore X, target underscore Y is equal to, and then this is going to be self.path at the self.current point index. This is getting our target point. Then I'm going to calculate the difference in X. I'm going to say the X diff is equal to the target X underscore X minus the self.X. Then I'm going to say the Y diff is equal to the target underscore Y minus the self.y. Now, I don't care about the absolute value because my tangent function will actually handle any negative values here, and it can potentially give me a negative angle. We will handle the negative angles. The negative angle is just, going to, I guess, the right instead of the left or the left instead of the right. Doesn't really matter. Okay, so now that I have both of these, I'm just going to say if y underscore diff is equal to 0, then the desired underscore radian underscore angle is equal to, and I want to say 180, but I want this to be in radians. Sorry, not 180. I want this to be 90. And so in radians, this is going to be math.pi divided by 2. Because math.pi is 180 degrees, 2 math.pi is 360. So the reason for this is that if the y difference is 0, I need to manually set the angle because my equation involves a division of the y difference, and I can't have a 0 division error. So you'll see what I mean here. I say else the desired radian angle is equal to, and this is going to be the math.arc tangent, so the inverse tangent of, and then this is going to be this is going to be x diff over y diff. Okay, so this is going to give me the angle that is between my car and between the point. And then same thing here, this will give me that angle. So if we have no difference in y, then that means that we're horizontal, right? We're either 90 degrees or we're either 270 degrees. Now in this case, we'll just make it at 90 degrees because 90 and 270 are equivalent angles, not in direction, but in like the magnitude of the angle if you divide them. Hopefully that's making sense, but we just need to avoid having an over 0. So that's why I'm writing this line here. Okay, now that we have that, what I want to do is I want to kind of implement a clause here that's going to fix this angle slightly if a certain thing occurs. I'm being very vague, but let's just write it. I'm going to say if the target underscore y is greater than, so is lower down on the screen than self.y, then what I want to do is say the desired radian angle plus equals, and this is going to be math.pi. So the reason I'm doing this is kind of what I discussed before. We can potentially have a problem where the angle that we calculate is it's always going to be an acute angle, right? And so if the target that we're looking for is actually lower down on the screen than where our current car position is, the turn that we need to make is more extreme than what the angle is that we're getting. Maybe we're getting an angle of 25 degrees, right? And the reason we're getting 25 is because 25 kind of spans this whole horizontal line. And so we're looking at it like this, but what we really want is to add a whole math.pi, add 180 degrees to it so that we go in the complete opposite direction of what the angle is that we calculated because we're going down. Because remember, we're always going to get an acute angle, so we're always going to be going kind of this way or this way, so we need to figure out if we need to go the opposite direction down. Now, in that case, well, the case is this. If target y is greater than self.y, we're going down, so we have to add math.pi to the angle to ensure that we're going to go the correct direction. I'm sure this is confusing, but that's really the best way that I can explain it. I'm not a math professor, and I don't want to get too much into it because I'm sure I'll butcher the mathematical explanations of all the angles. Anyways, there we go. Okay, so that's kind of the first thing that we need to do. Now that we have that, though, we're going to say the difference in angles is, or just angle actually, is equal to self.angle minus, and then the desired radian angle. Now we need to first convert this to degrees. So we're going to say math.degrees like this. Okay, so remember, this is going to give us the angle in radians. So then we convert it to degrees, and then we take whatever our current angle is and subtract it by whatever the desired angle is to get to. And then based on if this number is positive or negative, we're going to know if we have to move left or right. Now, another problem happens here. What if the difference in these angles is really massive? What if it's 270 degrees? What if it's 290 degrees? In fact, what if it's anything larger than 180 degrees? Well, if the difference in the angle is larger than 180 degrees, we are going to be taking an inefficient route to get to the angle. So let me show you what I mean. If I go to Paint here and we zoom in, so let's go, come on, zoom in. Control plus, does that not zoom? Okay, let's just move this. Okay, so let's say we have this example here, right? Where we have some angle here, and actually let's just do one here. And then we have another angle here. Now, if we calculate the distance between this angle, or the difference between these angles, maybe we get something like 220 degrees, okay? That's fine. But if we were to go in this direction to get to this angle, we need to travel 220 degrees. Whereas if we go in this direction to get to this angle, then we have to only go 140 degrees. Is 140 degrees correct? Yeah, 360, yeah, 140. I think that's right. Okay, so we only have to go 140 degrees. So obviously we would prefer to go 140 degrees than to go 220. So what are we going to do if we have an angle that's greater than 180 degrees? Well, if we have an angle greater than 180, we know we're taking an inefficient route. So all we'll do is we'll take this angle and we'll subtract, so let's say it's 220, we'll subtract 360 from it. Now you might be saying, well, why don't you do the other way? The reason I'm not doing it the other way is because I want to actually get the negative angle by going backwards. So if I have 220 by minus 360, then what I'm going to get here is negative 140, which is what I want, because I don't want to go 140 degrees this way. I want to go the other direction 140 degrees. So that is how I'm going to kind of fix this problem of potentially turning the wrong direction, is I'm going to simplify this, or I'm going to do this check to make sure we're going in the right direction. Okay, so anyways, we have the difference in angle, and now we're going to say if the difference in angle is greater than or equal to 180 degrees, then we're just going to say the difference in angle minus equals 360. So now we'll turn the opposite direction. So now that we have calculated the difference in the angles, we don't even care what the difference is. Well, we actually will use it in a second, but we just want to move in the right direction now to get towards the angle that we want. So we're going to say if the difference in angle is greater than 0. So if the difference in angle is greater than 0, notice we're having our angle first and then the angle that we want to get to. We want to go the other way. We need to go to, I guess, the right as opposed to the left. And the reason for that is when we go to the left, we increase our angle. If our angle is already greater than the angle that we desire, we need to go the opposite direction to get to that angle. So we're going to say self dot and then angle is going to be minus equals, and this is going to be the, actually, let me check here, the minimum of self dot rotation velocity and then the absolute value of the difference in the angle. Let me check that that's all good. Okay, yeah, that's what we want. So the reason for this is that I don't want to potentially pass the angle going the other direction. So let's say the difference in the angle is 3 degrees and my rotational velocity is 4 degrees. If I just straight up go 4 degrees to the right, I'm going to pass by the angle that I want. And then what's going to happen is I'm going to pass by it, and now all of a sudden I'm going to be 1 degree less than the angle that I want. And so I'm going to have to move back the other way. But I can only move by my rotational velocity, so I'm going to move back by that. So what's going to happen is you're going to be like stuttering back and forth, like left, right, which you don't want. You want to just be, steadily on the angle. So the point of this kind of min right here is that if the difference in the angle is less than the rotational velocity, we'll move by that amount. So we snap precisely on the angle. We aren't going like above the angle, below the angle, above the angle, below the angle. That's the point. Okay, so now that we have this, we're just going to say else, because if it's not greater than 0, then it must be less than or equal to 0. And here, we're just going to swap this to a plus. Now, I think we can just leave the exact same thing in here. Yeah, we can. And that should actually be good. That will actually rotate our car so that it's going to move towards the point. So that is kind of the trickiest part right there. This very complicated method, I'm sure this doesn't make 100% sense. Doesn't have to. If I'm being honest with you, I don't understand it 100%. This was a lot of trial and error to get this to work, but hopefully what I explained gave you some sense of why we're doing the things that we're doing. Angles are difficult. That's the moral of the story and of this tutorial series. Okay, continuing. Now that we have that, what I would like to do is I would like to make sure that we move to the next point in our path when we are ready to do that. So I'm going to say define update underscore path point like that. And then inside of here, all I'm going to do is check for collision with the points that we have. So whatever point I'm currently on, I'm going to see if my car has collided with it. And if it has collided with it, then I've hit that point. We can go on to the next one. So let me just look at my cheat sheet right here. Okay, that looks good. I'm going to say the target is equal to, and this is going to be self.path at self.current point. I'm then going to create a rectangle from my car. Yeah, that's what we're going to do. We're going to say rect is equal to Pygame dot, and then this is going to be, I guess it's just rect. Yeah, I think it is just rect, pygame.rect. And then we're going to, instead of doing target, I'm going to say self.x, self.y, and then we need to get the width and the height of our image. So I'm going to say self.img.get underscore width and self.img.get underscore height. So the point of creating this rectangle is that my image alone is a rectangle, but it doesn't know its location, right? Like the image doesn't know where it is. So I make a rectangle using the X and the Y of my car as the top left-hand corner, and then I get the width and the height of my image. So now what I can do is use a built-in method in Python, in Pygame, to determine if a point is colliding with my rectangle. Now this is pretty intuitive, but it is collide point like this. And all it does is take a point. So you have to call this on a rectangle, but it takes a point, which will be target, and tells you if you are colliding with it. Now, in fact, it actually takes a X and Y coordinate. So what I'm going to do is pass asterisk target, which will then pass the X coordinate and the Y coordinate as separate arguments to this function. If that's the case, if I am colliding with that point, I'm going to say self.current point plus equals 1. So if we've hit the current point that we're going to, then let's move to the next point. That's the idea behind update path point. Now let me just look and see if I've messed anything up. Everything looks good to me. What we can actually do now is we can start running the car, like moving the car around, and you will see that it will start moving on the path. So let's see how to do that. Again, I have to reference my code here. Okay, it was easier than I thought. We're just going to say computer underscore car dot move. Okay, so just like we have move player, now we have the move car. So let's do that. Let's run our code after we move our car. Let's cross our fingers and let's pray this works. And notice our car is zipping around the screen here and it's actually following these points. Okay. Now you will notice that sometimes it might kind of hit the edge, right? So you just saw right there, it almost hit the edge of the screen. Keep in mind that it is aiming to get its top left-hand corner on all of these points. So that's why it's taking these kind of wide turns. You'll notice that the top left-hand corner of the car is what's kind of aiming to intersect with some of these points. Okay, so we just ran into a problem there with this point right here. So that is most likely due to the fact that that point was too close to this one right here. And so we couldn't actually hit this point. We couldn't intersect this point from this one because we couldn't turn quickly enough. So what I'm going to do is kind of fix up some of these points, and then I'll be right back. Notice we're getting another problem here. So in fact, let me just look at this and see maybe where I made a mistake, and I'll be right back. So the problem is what I expected. The points that I have are just too close together, so the car can't actually hit it. Now that will be fixed by lowering the velocity of the car because it can turn quicker than it can move. But to fix this, we just have to remake the path. So I'm just going to remake the path. I'll be right back. I'll show you the new path, and then hopefully we should just be all good. All right, so I've just recreated the path here. Now I'm not going to lie, it's not perfect. It goes off the screen a few times, not very badly, but anyways, point being, I recreated the path. You guys know how to make the path. I showed you the code to do that. It's pretty straightforward, so you can mess with it and design as many times as you need to. Now, based on the way we have it right now, if you just clear the path at the start and then you add values to the path, the car will actually follow up until the last value in the path. That's the way that we've designed it. So every time I was clicking, it was actually going to that point, which was kind of cool. You could see how it kind of traced the path in real time. Now, one of the big reasons why it's hard for the car to actually hit some of the points is because of the turning radius, right? If you increase the rotational velocity, then you won't have the same problem that I'm having here. Just because it needs to take kind of a wide turn to be able to get to some of the points. Now that's going to change with speed, so you have to be careful. If you have a lower speed than your rotational velocity, it's not necessarily higher, but you can just turn more because you're not moving as quickly to each point. Anyways, I just wanted to point that out. Okay, so now I have this new path. So I'm just going to copy that into this path variable here. So let's get rid of all that. Let's paste that. And now let's repass path. Where is it? Right here. So I'll just show you what I had was I just added this code back in, and that's how I was able to recreate the path. And then I had just cleared the path previously. Okay. All right, so now that we have all of that, our computer is going against the player. So what I want to do now is get rid of the drawing of the path. So I'm just going to go and comment out under draw this self.draw points because I don't want to do that anymore. And I want to implement some collision between the computer and the finish line, just so I know if the computer gets to the finish line first. And then in the next video, we'll implement all of the level stuff, but this will just be kind of a nice thing to finish off right now. Okay, so just like we have this, the finish POI collide, I want to go player underscore, and I just want to preface this all with player because I'm going to do the exact same thing now, except with the computer. Although with the computer, I know it's not going to hit the finish line in the wrong direction, so all I have to do is just see if it hit the finish line, and then I know it crossed in the right direction. So I'm going to copy this, and I'll put it actually above here, and we can go like this. And instead of player, we'll just say computer. And then we will just change the player to be computer car. And now this will tell us if the computer has hit the finish line. So I can just do an if statement here, and I can say if the computer car computer underscore finish underscore POI underscore collide does not equal none. And then I can print out computer wins, exclamation point, because in this case, the computer would have gotten there before the player. Now, we do need to reset both the player and the computer if the computer does win. So I'm going to say player car.reset and computer car.reset. And that reminds me, inside of here, I also need to say computer car.reset because now if the player gets to the finish line, we need to reset the computer as well. Okay, we can get rid of the print statement. I'm not going to test this because I'm just very confident this is going to work. But what I'm going to do now is take all of this collision code, and I'm just going to put it in a function, again, just to kind of clean things up. So I'm going to say define handle underscore collision. Now, we want to take both the computer car and the player car. So I'm going to say player car and computer car like that. Now, inside of here, we'll do all of this, and then we can just call that function. So I'll say handle collision, and then we'll pass the player car and the computer car, and let's just run this here and let's test and see. Yep, okay, I can hit the walls just like I was before. Great. So there we go. That is all working. And with that, that's going to end this video. So we're getting very close to finished here. We just haven't implemented the logic for the game and the nice text. So in the next video, we'll do all of that. But this is the hard stuff. What we're doing going forward is very simple. We just need to keep track of what level we're on. We just need to reset the cars in, the correct way. And yeah, all that stuff's pretty easy. So we'll wrap that up in the next video. If you enjoyed, make sure to leave a like, subscribe to the channel, and I will see you in another one.